All right, in this lecture, we're going to go over Bayes' theorem and independence and something called the law of total probability. So these three things are really important concepts that we'll use as we work towards this idea of creating the naive Bayes classifier, which is a type of machine learning algorithm. And probability questions are always, they can be very tricky because it's hard to get into the mental space to think about things, and a lot of the time questions yield very unintuitive results or require an unintuitive way of thinking perhaps. So some of the best ways to get comfortable with probability is to do problems. There's a couple of those problems that Suraj recorded, and those are linked on the website. Those are good. This textbook, Theory Meets Data, is just a different way of explaining some of this probability stuff that we're learning, and that can be very good. It's a big reason why we do a lot of the tutor questions live in class and solve things, is because it's great to hear other people's way of explaining stuff. Sometimes it just clicks. And then Janine's probability roadmap, those several PDFs are really a document to go through to have sort of a recipe for approaching probability problems. Okay, so let's start off with the law of total probability and thinking about how we can use it to solve some problems. So this is the example that we'll be using for the next several slides, and it's a survey that we conducted at school where we asked students two questions. How did you get to campus today? And that's either a trolley, bike, or drive. And these are the only three options that exist in this world, let's just say. Those are the only three possible things that students could do. And then if you were late or not. So that's the questionnaire that we asked. And particularly, all of these 6 boxes, you'll notice if you take them, they all sum up to 1. So that's a very important concept because that is a probability space. And the idea of a probability space will become very useful when we start talking about partitions in a few slides. And that will be something that we use as we build towards Bayes theory. Okay, so that's all of these add up to 1. And the next important thing to think about is how do we express each of these? Because taking the trolley, taking the bike, or driving is sort of a part of our sample space. And then whether you are late or not late is sort of an outcome of being in one of those parts of the probability space. So what do I mean by that? Well, the value right here is 0.24. What does this actually mean? So it's the probability that you took the trolley and that you were not late. And we have this one for drive. And this one is the probability that you drove and that you were late. So one key thing, and I'll write this a few times because sometimes it takes a little bit of time to click. This symbol right there is the intersection, and that's just a way of saying and, because it's the people who took the trolley and were not late. So it's the intersection between those two things. Okay. Let's try and answer a really quick question. What is the probability that a randomly selected person was late. And at this point, this is not a tricky question at all. It's exactly what you might intuitively think. So take a few seconds and think about it, and then we'll solve it. Okay, let's start by kind of summing up some of these rows and columns. So we can say that this equals 0.3, and this is the probability that a student took the trolley. This one is 0.1, and that's the probability of taking a bike. And this one is 0.6, that's the probability of driving. And then this one is 0.55, and that's the probability of not being late. And this one is equal to 0.45, the probability of being late. And remember what we said before. For example, the bike, this one is the probability of taking the bike and being late. All right, so when we say what's the probability that a randomly selected person was late, well, the answer is simply just taking a look at this row or this column and then summing them all up. So that's going to be 0.45, because you're either late or you're not late. So the probability that a randomly selected person who took this poll or the survey was late would just be 45%. So that's not difficult at all, and it's not supposed to be a trick question, but it's an important concept to think about, because if we kind of break this down a little bit more, what we have here is a probability space, and we can actually draw this out. This will be important to, we've kind of seen these before. So this is our probability space S, and in here we have 3 outcomes, and those outcomes are you either took or we have 3 partitions. You either took the bike, the trolley, or you drove. And these numbers were 3, 1, and 6, so I'll try and my best to kind of do that. 3, 6, and 1. Okay, so something kind of like this, where this is, maybe I'll get black. Drive, bike, and trolley. And then in here is some outcome. So let's draw a circle. And everything inside of this circle is the probability of being late. That means everything outside the circle is the complement of being late, which is not late. So we can actually draw this. Like so. Okay. So, since everyone either took the trolley, the bike, or drove to school, we have the probability of being late, which we already calculated, which is 45%. So this was 0.45, but what does that really mean? Well, if we look at our probability space, we can kind of pull out these intersections, and particularly when we say the intersection, we mean the intersection of all these individual probability events. So the probability of late and taking the trolley means that we're late, so we know we're already in the circle, and we know we took the trolley, so we're in this box, and so what we're looking for is the intersection between late and trolley, which is this area right here. So this was done with purple, so the probability of late and trolley is 0.06. So that's 0.06. And that was the area that kind of looked like this. And then we had late and bike, that was green. So this is 0.03, and that was the area that looked like this. And the last one that we had was late and drove, which would be 0.36, and this was the area that looked like that. And where these percentages come from are, since we're concerned about being late, right, it means we're going to be in this column, and then these values just are going there. So that's how we get the total probability of being late as being 0.45, because it is the sum of all these individual intersections between being late and having taken any mode of transportation. So this is how we kind of look at a probability space and can use it to sum up individual events that can lead us to having a probability of something like being late. Okay, so let's try and answer another question. So surprise, surprise, Avi the avocado is back in full force. So this question is, we did our poll and our survey, and of course we asked Avi because we care about Avi's opinion and we're self-selection biased to Avi. So Avi took the trolley to school, and we want to know what is the probability that Avi was late. Now, this is also not a trick question, but this has a very tricky there's a logical step that you have to take. If not, you'll get hung up and pick the perhaps maybe intuitive idea. And so I'll give you a few seconds to think about it, and then we'll answer this question. All right, so if you're looking at this table, you're like, okay, what's the probability that he was late? So I see that Avi took the trolley and he's late, so 0.06. Boom, answer's A. And that's not like it is the incorrect answer, but logically it makes sense because we're looking at all this information and we say, okay, look at the table. However, the reason why that's wrong is because we have this given right here. Avi took the trolley to school. That means that we don't care about any of this stuff down here. This no longer exists in our probability space. Our new probability space is this right here that we really care about. And the probability that he is late requires us to think about just this stuff. So maybe I will highlight this to make it apparent that this is the stuff that we now care deeply about. So let's go ahead and start to work on a solution for this. So we have the We'll just do it here. The probability of late given trolley. And wherever we have the, it's just another color. Whenever we have a probability of X, this thing, Y, that means given. So the probability of X given Y. That's what that's how you'd read that. Okay, so back to our problem. The probability of late given trolley is equal to the probability of late and, or the intersection, and trolley, and that's going to be over the probability of taking the trolley. Now then, the probability of taking the trolley is really just this entire column, or sorry, this entire row. But we can be a little more explicit to help think about this. So let me just move this over. I think I want to keep this here. I think I'm going to rewrite it. So this is now equal to, we have the same numerator. And let's rewrite our denominator. So now this is the probability of two things. We'll add them. So what are the two things? Well, the probability of having to take the trolley is the probability of having taken it and being late and not late. So this would be late and trolley, and not late and trolley. So let me just, so we're running a little bit out of room. Here, L equals late, and L equals not late. All right. So, what does this equal? Well, we can just fill in the probabilities now. We know the probability of being late and taking the trolley is 0.06. We get that from there, over the probability of being late and the trolley, again, is 0.06, plus, we'll do this in blue, the probability of not being late and trolley, which is 0.24. So this is just equal to, same thing as saying 6 over 30, which is equal to 1 over 5, which is equal to 0.2. Sometimes it's easier to think about this stuff not in terms of decimals, but just going back up to whole numbers, because the probability of 1 is the same thing of doing it out of 100. But we don't want to say this is 20. We want to go back into being in decimals and say 0.2. So that's how we get our final answer of B. Now then, that should hopefully be an example of how what might be the intuitive quick thing to say, 0.06 was the answer. If we really think about it, it's not the answer, because we have to look at the problem that we're trying to solve. And the problem we're trying to solve is just, what's the probability that Avi was late? And the important thing is that he took the trolley. So it's a given he took the trolley, not given he took the trolley, bike, or drove. Like, let's say we didn't know, then what's the probability of being late? That would have just been 0.45 again, because if we didn't know what mode of transportation he took, then that's just the probability of being late. But we know what that mode is. So the probability of being late is based on not being late and based on how many people actually took the trolley versus not, which is why the denominator has this whole thing kind of baked into it. Okay, so let's try and write this in a little bit more formal terms, because what we're trying to build towards is a general way to express these type of probabilities, and that's the total law of probability. So how do we do that? And we've already started to do it a little bit, and maybe it's just a really good refresher. This symbol is and. It also is the intersection. So because everybody either takes the trolley, bike, or drives to school, we can express the probability of being late as the probability of each individual event happening. The probability of being late given every individual mode of transportation. And we can also express these things in a different way. And this will become a very important concept because we may want to rearrange our expressions based on the information that we are given. So for example, and this will be sort of just a follow along, and then hopefully it will make sense as we start to do some problems. But let's take, for example, the probability of being late and bike. So how do we rewrite that? Well, one way to rewrite that is the probability of bike given, the probability of bike multiplied by the probability of being late given that you took the bike. So these are essentially equivalent statements. So why is this important to be able to express it this way? Well, we are going to need to express these type of probabilities in terms of the second form when we get into Bayes' rule, especially. And these are important ways to think about the probability because it puts the emphasis on a condition. So it's no longer just the probability of late and you took the bike. It's now the probability of having taken the bike multiplied by late given bike. So it's conditioned on the fact that you took the bike, because being late is, it's whatever, but this probability of being late is conditioned on the fact that you took a bike. And let's see. So, yeah, I think that's good for this slide. We can say that. Well, what this is really building towards is and maybe this will make a little bit more sense. We kind of bring the actual definition in. So what we've been looking at here, like exactly this, is a probability space, but we really are trying to build towards something called a partition. So let's kind of put this idea on ice for a couple of slides, and let's talk about this idea of a partition. So if we have a set of events, it's E1, E2, all the way to EK, and the events are having taken the trolley or taken the bike or driven a car, right? So like these are events, or these are the equivalent events, the outcome being late or not late. So if we have some k number of events then it is a partition of our sample space S. That is, that each of these E's is a partition of S. I'll just write this. So S is our sample space. It's a partition of S if two conditions hold. One is that the probability that some part of your event I and EJ equals 0 for all pairs of I doesn't equal J. So what this is really saying is that you have exclusive events. That is, for like example, just to stick with our example that we've been doing, you can't both drive and bike to school. Has to be one or the other. Right, so that's what the first part of that is saying. So they're exclusive events. The second one is that the probability of the intersection between all of your events, K events, right? So these are the intersection between, or sorry, not the intersection, the union between all of these. So let me also just make that clear. If this symbol equals intersection, in other words, and then this one equals, or is union, which is another way of saying or. So the union of all your K events has to equal 1. So the probability space needs to be equal to 1. This would be like, for example, flipping a coin. Flipping a coin can either be heads or tails, and if it's a fair coin, both are 0.5 plus 0.5, which equals 1. And an equivalent way to also say this is the probability of the sum of the probabilities for each individual event E up to the number of events you have K must also equal 1. So union, same thing as saying plus here. So we can express like the probability of being, like, so going back to our example, it would be the probability of being late would be a sum of the products involving the conditional probabilities. So that which would be all of these, or could be expressed as all these. All right, so this is probably, it probably makes sense, but to solidify it, let's do the pretty picture principle and draw a picture. So when we say your KEs form a partition of S, that says that every outcome is in exactly one and only one event. So all of the students that we polled, right, for the survey, each one of their outcomes, being late or not being late, and whether they took either the trolley, the bike, or they drove, all of their outcomes, which make up these probabilities, right? Because these probabilities are based on counts. Like if we sampled 100 students, 36 of them said they drove and were late, and 24 said they drove and were not late. Every one of those students that we sampled has to be in one of these boxes, and particularly one of these partitions, right? Because you could have a student that would be in drive, but they could either be late, or they could either be late or not late, but they can only be in drive. you can't have a student that does like that, you know, or God forbid that, or this. They're either here, 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 or here. Those are the only 6 possibilities. So let's go ahead and kind of draw what that would look like, which we already kind of have, but it's good to see it again, because keeping this picture in your mind is a really great tool for being able to get a handle on the probability space that you have when you're trying to solve a question. So this is our probability space, and we can say that we'll use red, and x equals an individual outcome. So write this a little bit better. So for example, and late. Okay, so let's divide up this space again. Let's kind of make a little. Let's in this picture we kind of stuck to the example that we had. Let's make it a little bit more general, because what we're trying to do is to create a generalizable framework here. So let's just assume that we have. I like to draw boxes, but some people like to do probability spaces that look like this, because maybe it's a little bit easier to think about the probabilities. Doesn't really matter. 1, 2, 3, 4, 5. Let's do one more down the middle. Okay, so we have 6 areas, or 6, yeah. So we have here, this would be like we have you know, K numbers. This would be like E1, E2, E3, 4, 5, and then E6. And then we have a bunch of outcomes. We have here, here. Okay. And again, it doesn't really matter so much. What we're trying to show is that there's some probability space that is divided up or partitioned into different individual exclusive E events, numbering K, or with K number of events. And then we have individual outcomes that occur within partitions. You'll see I don't have anything like this. These would not make sense. So they all have to be inside one of them. So if we could say, maybe make it a little more explicit. So for our outcomes, which are these x's, we have 2 principles. One is that, I guess this is also for our outcomes and our E of K's. In red, we have 2 outcomes, so no E overlaps with another E, so we don't have anything where we have something like this, where this is like E1, E2, and E3, where E3 overlaps with E2 right right here. So none of that. This we can't have. No overlap. Okay. The second principle that's important is that every outcome every outcome X is in one and only one E. So those are the two main things about a partition that we have to have in order to have a valid partition for your event spaces. So example partitions, because it's good to have a feeling for this, because this is going to map onto the questions that you're asked eventually, are, for example, we have the trolley, biking, and driving. These are all independent. You can't do both. I mean, sure, you could bike to the trolley station and then take the trolley, but in our world that we had set up, you can only do one of those three things. So in getting to school, events like being late and not late. So those are valid events, and you're either late or you're not late. Selecting an undergraduate student at random. So in our example, in our class, we might, other would be like a super senior, or a high school student. So you're either freshman, sophomore, junior, senior. You're not like, both. I know the concept of like a rising senior or whatnot, but if you're either right now a freshman, a junior, or sophomore, one of those. Rolling a die. The die is either going to be even or odd. Can't be both. Can't have an eaved or an oven. That would actually be a better one, right? It's either even or odd. No oven or eaved. Drawing a card from a deck. Could be a spade, club, a heart, or a diamond. One of the four. Those are card suits. So another one would be a special case. Any event A and its complement. Sometimes it's also or its complement. So for example, like late and not late, you could say like late's complement is all students not late, which in reality is people who are, on time or not late. But, the complement of late isn't not late. Technically, the complement of late is, you get late and not late. You're either late or you're not late. The complement of late is technically 1 minus late, is what I meant to say. So one thing we want to keep in mind, because it's kind of like an important idea, maybe we'll draw a little area. So if we have, let's say, events A, B, and C, and they are pairwise mutually exclusive events, but they're not a partition. It is because the probability of A plus the probability of B plus the probability of C do not equal 1. So an example of that would be if I had something like this, and this is our space, and we have A, B, and C. We're kind of really missing all this area around it, right? Like this is different. So this is not equal to something where we'd have like A, B, and C. And the reason why is pairwise mutually exclusive. So in that case, that does not form a partition. You know, this is not a partition. This is a partition. And really think about the word partition, you're partitioning the environment. That'd be a good way of thinking about it. Okay, so this all gives rise, this is what we've been building towards, the idea of the law of total probability. So we've already technically seen this with the trolley problem, but we'll rewrite that in a second. So if A is an event and we have K, E's that are part of our partition or make up a partition S, then we can express the probability of event A happening as the probability of A and E and the probability of A and E2, so on and so forth to our K, E. And so the probability of like, just to, we'll do this in blue. So just to kind of provide the, the showcase that we've already done this would be like saying the probability of being late is equal to the probability of being late and trolley plus the probability of being late and drive plus the probability of being late and bike. And in this case, our A is late, that's the event, and the partition of our sample space are our E's, and that is going to be trolley, E2 would be drive, and E3 would be bike. And we can sum this, we can express this in our notation that we have here as the sum of the probability events from I to K of event A and the partition of E occurring. So that is the law of total probability, and this is an extremely important law, and it's something that we're going to use a lot in solving problems. And particularly, if you remember, we can take this idea of the law of total probability and we can rewrite things in terms of conditional probability, which is this right here. And we'll see more about how this connection happens. But in the meantime, let's take this image here. I think I can copy paste this. Yeah, let's just set this in the corner. Okay. So let's take this idea of the law of total probability and show a generalized form of this with our partitions in our sample space. So we have, do this in blue, we have our probability of A equals the probability of A and E1. Now we have 6 E's, so I'm going to plus, I'm going to do 2 more for a particular reason of A given E5 plus the probability of A given E6. Okay, and then real quick, I'm going to move this red outcome just down to there. Okay, so let's say that we have do this in yellow. I want to avoid E5. So we're going to do okay. So here is our probability of A. Maybe I should actually, well, I'll just draw a little box around it so we know. Interestingly enough, this doesn't include E5, which is fine. What I want to show is that E5 is not in there, so we can take E5 and you'll notice like nothing in E5, you know, E5 is in this thing. So this whole probability will be 0, and that's totally fine. But what we're really saying, and we can sum this up as the probability of A is equal to the sum of 1 to 6, because we got 6 E's, as the probability of A and our E's for each individual E. And what this is saying is everything, that falls under, should I use a different color? I think it'll get messy, but let's try it. Okay, so for E1, we have that whole area. So this is like E1, and then we'll do E6 in purple. And for E6, we have all this space, and then we'll just count the rest of these ones in dark blue. That's all of these ones that are hidden. So that's all this stuff. So this is how we formally define the individual probabilistic events that occur within each partition when a certain amount of the event A incorporates some amount of our partitions. It could also include all of them, like this. When it got to E4, it could have very well have also done this. This is like valid too. It all depends on the problem and what probabilities we already know, or what probabilities we're given, or what probabilities we're even assuming. And we'll talk more about that. Another thing to keep in mind too is this idea of a good way to explain this. So let me put a definition in. Let's say that we have the, not a definition, but an example. We have the probability of A or A and E1. So we can say that this is the probability of A times the probability of E1 given A. It's also equivalent to say the probability of E1 times the probability of A given E1. Now, the probability of A and E1 occurring can be expressed in both of these ways. And the reason why both these ways are important to be able to express the probability of these two things happening is because we want to be able to reformulate or rewrite the law of total probability, which this is very much a part of, in terms of conditional probabilities. And this really depends on what it is what question we're trying to answer. We're trying to find, in this example here, the probability of A. And so whether we choose to tackle the problem in this way or this way, well, the fact that we're looking for the probability of A means that we don't actually have this probability. So we need to might be better to consider looking at the problem this way, because we can figure this out with this information a little bit easier. And we'll see some examples of that coming up. And specifically, we'll redefine the law of total probabilities using so this is something called the multiplication rule here as a way to reframe this in terms of conditional probabilities. So that's where this came from over here. The reason why this statement and this is equivalent, which is what we have right here, is because of something called the multiplication rule. So we will explore this in lots of problems, but to formally state it, we can look at the law of total probability in two ways. The first way being the end approach, right? Because we have these and but this assumes that we know a lot of information, right? Like in order to actually use this to frame the problem with this type of expression, we need to have something, like this here. We don't often have this type of perfect information. So we need to be able to reframe this in terms of what's called conditional probabilities. So if we do it this way, this is conditional probabilities, because each of these individual things right here, here, and here are conditionals, right? A is on E2, given. That's what this little line there means. That line is given. Not 1 or L or I, but given. Okay. So let's go ahead and let's do a question. This will give some insight. So we have this chart here again, and Lauren is late to school. What is the probability that she took the trolley? So think about the law of total probability, and then we'll come back and answer this question. Okay. Let's see. We know that from, I believe it was the last one we did. Yes. The probability of being late, given you took the trolley, was 0.2. So now we kind of want to ask the question, what is the probability of trolley given being late? All right, so the probability of trolley being given that you were late. So if we know that you were late, what's the probability that you took the trolley? A little backwards way of thinking about it. So here we have the probability of trolley and late over probability of being late. And this is equivalent to saying for this will get a little bit messy. So we're talking about being late. So we have this one, and we'll use blue for bike, and we'll use green for drives. Okay. So here we have the probability of trolley and late over. So now we're going to do the same one as before. So the probability of being late incorporates all of the trolley, bike, and drive. So we'll just take this one at a time. This is the I'm going to use a shorthand of trolley and late plus the probability. Let's do the bike now. So the probability of bike and late plus, now we're on green, the probability of drive and late. So we know that the probability of trolley and late is going to be 0.06. So this will equal 0.06 over 0.06 again. And then we have two more numbers that we need to add. So for the bike, that's going to be 0.03. And for drive, 0.36. And we can say 0.06 over 36, 39, 45. So 0.45. And we can say this is like saying 6 over 45, which is about 15 or so. So 0.15. Yeah, we can scale these up. Okay, so yeah, this answer is going to be about 0.15. So this will be our answer here. So let's go ahead and talk about Bayes' rule now, and particularly we'll revisit this concept here, which is how we're able to get these two conditional forms of the end form of this probability. And this is through something called the multiplication rule, which we'll see in a slide coming up. But it's really just allowing us to reframe these probability events as conditional probability events. And again, this is done via the by the multiplication rule. We can go from this to this. Okay, so let's go ahead and see how that works. So we often don't have those nice tables with all the probabilities in them. I mean, particularly like this table. We often have incomplete knowledge. We might just have the probability of being late, the probability of taking a trolley, and the probability of being late given that you took the trolley. And we want to know, can we still find the probability of taking the trolley given that you were late? And maybe we can actually write these down. So in this case is like a generalized form. Here we're given the probability of A given B, and we want to find the probability of B given A. So that's what we want to get out of this. And we will do this we'll accomplish this via the multiplication rule. So what does this look like? Okay, so we want the probability of taking the trolley given that we were late, which is going to be in the form of the probability of taking the trolley and being late over the total probability of being late. Now, we already have one piece of information here. We have the probability of being late, and that's given to us right up here. So we can go ahead and use that. And we're going to need to use the multiplication rule and apply it carefully in order to get this part, because we don't have this n. We need to put it into a format of conditional probability. Remember, we don't have this, but we can use the multiplication rule to get it into this form. So this can become this. So let's go ahead and do that. So this is going to equal, we still have the probability of being late down below. Nothing changes there, and nothing changes. I'll just re-highlight it. But now we have the probability of taking the trolley, which we have, times the probability of late given that we took the trolley, which we've already calculated before as being 0.2. We did that from that question. So we already have this, and we already have this. So we can just rewrite this now as 0.3, the probability of taking the trolley, times the probability of being late given that you took the trolley, over the probability of being late, which is one of our givens, 0.45. And this will equal 0.3 times 0.2, 0.06 over 0.45, which is going to be like saying 645, 6 over 45, which is, yeah, a good enough answer as the probability of taking the trolley given that you were late. So we know that you were late. What's the probability that you took the trolley? And we did that with the careful application of the multiplication rule, because remember, the multiplication rule states that if we want P probability of A and B, we can rewrite that in the form of the probability of A times the probability of B given A, or we can put it as the probability of B times the probability of A given B. And the carefulness in the application of the multiplication rule is deciding which one of these that you want. And often it's the one that might seem less intuitive but mathematically makes sense, as being the one that we want to get. In this case, trolley is our A and late is our B. Or no, I'm sorry. Well, yeah, that's true. Trolley is A and late is our B. So it wouldn't make sense to have, it makes sense to write it in this format here, which is what we did down here. A and B and A, which we got from A and B. The reason why we wouldn't want to do the probability of, well, we'll see that in the next example. So let's move on before this gets too much on the slide. Okay, so Bayes' theorem, this is what we've been working towards. Bayes' theorem, also sometimes known as Bayes' rule. Is really a way of looking at probabilities and being able to have an expression that we can rearrange to evaluate probabilities that are either in the conditional sense or the end sense. So yes, it does allow us to do that. And it relates to the law of total probability, which we'll see as we work through these next two slides. Let's see. So we have the multiplication rule here, and we also have it written here, and we can show that these two things are equivalent because probability of A and B is equal to the probability of B and A, right? So these things are functionally equivalent. So because these things are functionally equivalent, we can write this expression here. Probability of A times the probability of B given A is equivalent to the probability of B times the probability of A given B. And then we can rearrange this equation by subtracting out the probability of A from both sides. And that gives us the probability of B given A is equal to the probability of B times the probability of A given B over the probability of A. And this is a theorem which does a lot, but one thing that's very useful about it is it allows us to kind of reverse engineer conditional probability problems. So, and that's a consequence of being able to rearrange the equation and substitute in different types of conditional probabilities based on the information that we're given. Because many problems won't give us the probability of B or the probability of A given B. Well, actually, a lot of them will probably give us the probability of B in this case. So we will usually have this information, and we'll usually also have this information. But what we don't often have is the probability of A. That's the thing we're often missing from these kind of questions. So Bayes allows us to sort of reverse engineer conditional probability questions. Okay. So let's kind of look at Bayes' theorem and how it applies, or maybe how it relates to the law of total probability and the idea of sample spaces. Okay, so here is Bayes' rule as the formal definition that you'll see like in textbooks and whatnot. This is definitely worth remembering. And as a, well, let's start by drawing a sample space. So here we have our sample space, and it's divided up into two. One is B, and one is the complement of B. And we have some event A, and A occurs like this. Now, B and the complement of B make a partition of our sample space. And we can use Bayes' theorem to kind of think about this concept a little bit. So let's go ahead and write this, put this in blue. Maybe we'll write that up here. Yeah, so we have the probability of A is equivalent to the probability of A and B plus the probability of A and the complement of B. And this makes up our sample space of our event, the probability of A right here. So we have B and the complement of B, that's our partition. And we can use the law of total probability to rewrite the probability of A, which we've done. We have the probability of A right here, and we can go ahead, and that's what we have right here. We can go ahead and use the multiplication rule to rewrite these. Right here. So using the multiplication rule. And what these things represent is this right here, the probability of A. So we can effectively rewrite Bayes' theorem a little bit into this new form down here. We have still the probability of B given A. That's what we're trying to find. And we still have the probability of B times the probability of A given B. That's in our numerator. And we've rewritten the probability of A down below in terms of the probability of, using the multiplication rule, in terms of probability of B times the probability of A given B and the complement to that. So why is that useful? Well, we often aren't, so okay, let's write this down. So why? Well, we are not often provided or know, and this is not just in probability problems, but also in real life problems. We often are not provided or know the probability of A. So we have some way to kind of sneak up on it and calculate it. And by using the ideas of partitions and the multiplication rule to get into conditional probabilities, we can take the probability of A and recast it as this expression here. And we can usually find out what these things are because we often know what both of these are. We often know the probability of some event B and the probability of A given B we can find out. And if we can do that, then we can also do that down here. And this is what gives us our probability of A. And if we can figure out both of those, then we can use that to determine the probability of B given A. So this is a little bit probably abstract, and that's perfectly fine. We're going to work through three kind of weighty problems that will give us a good opportunity to see this in practice. So maybe I can just also put this here, put that there, and put this here, because these are the three things that are being tied together. And this is what allows us to solve for the probability of A, which we normally don't have. Let's try this example. And the one of the key things in this example that we'll kind of go over is this idea again, because I think this is can be kind of difficult to understand. So a manufacturer claims that its drug tests will detect steroid use, and let's just assume that the numbers that they give are quite good. Let's say that 95% of the time it works. What the company does not tell you is that 15% of all steroid-free individuals also test positive. So the false positive rate. So 15% of people who do not use steroid will still test positive when taking this test. And suppose that 10% of the Tour de France bike racers use steroids and that your favorite cyclist is tested positive. So let's highlight some stuff, and we want to know what the probability that they use steroids. So really quick, it's always good just to highlight numbers just so we have that. Okay. The hardest part in probability questions, especially ones like these, is never going to be the math. The math is always going to be super simple, arithmetic essentially. The hardest part is always assigning what numerical values go to the A's and the B's, and what A and B actually even represents. So let's start there. We have A and we have B. So A, we're going to call, is a positive test. So positive test, no other information, just a positive test. And B is going to be the person that the cyclist actually uses steroids. Now then, we need to determine a few things. The first thing we need to determine is the probability of A given B. And then we need to determine the probability of A given the complement of B. And then we need to determine the probability of B. And what we want to find out ultimately this is what we want to know ultimately is the probability of B given A. So that's the goal. Okay, so what do these actually mean? So the probability of A given B is going to be equal to 95% of the time. And actually, before we do that, let's color code all this stuff, because that'll make things at least a little bit easier to, or hopefully a little bit easier to follow. Okay. So the probability of A given B is going to be 0.95%. So what does that mean in plain English? Let's highlight that. So in plain English, that's going to be that we have a positive test given A, given B, B being that the cyclist actually uses steroids, given uses steroids. Because that's what the test is saying. 95% of the time it works. If you're using steroids, then 95% of the time you're going to get a positive result on our test. So that's the true performance of their test for catching people who use steroids, and that test is highly sensitive to that. Now, what we want to know, though, is how many people who don't use steroids are going to get caught up in this as a false positive, because if that rate is high enough, then we would expect a lot of cyclists who are innocent to get flagged. And so we want to be able to know what that percentage is going to be. It'd be very important. So what does this equal? The probability of A given the complement of B is going to be 0.5, and this is our green. So what the company does not tell you is that 15% of all steroid-free individuals also test positive. So in other words, we have a positive test given a cyclist does not use steroids. And let me just rewrite that a little bit. Test. Okay. And then we have the probability of B, which is 0.1. This one is quite simple. It's just the prevalence of steroid use on the tour. Now, in the real world, this winds up becoming sort of a belief that we have about the real world. And it typically is never going to be 100% correct, but it ought to be a very good educated guess about the real world. And that number could be derived either from looking at historical records and saying, like, what's the prevalence for steroid use on the tour, or it's got to be some sort of intuition, though, baked in. It can't just be a completely random guess. So what this is saying is how many cyclists, percentage I'll say on tour, but in Tour de France, use steroids. So this is the real steroid rate. Okay. And what we want to know is the probability of B given A. And maybe let's just rewrite this a little bit. Real steroid rate. Okay, so what we care about is the probability of B given A, so that the and really what this is kind of saying is that, oh, the cyclist tested positive. Well, how likely are they to actually use steroids? So it's sort of the way of trying to think about how likely is it that the cyclist is actually actually cheats, given a single positive test result, which we would expect to be lower than this because this test is highly sensitive to trying to catch people. The worst mistake you can make here is a false negative, and that's telling somebody who actually takes steroids that they don't take steroids, because then you have people that are slipping through. A less costly mistake is to tell somebody who doesn't use steroids that you do use steroids, because you just take a few more tests, and then that should, they would have not positive results, most likely in follow-up tests, which would then discount them. But if you are a steroid user, you should continue to have positive test results. So this is just for one test that each cyclist takes. All right, so let's actually solve this problem. Now that this is the hardest part, like what we've just done here. This is absolutely the most difficult part, because if any of these numbers that you have don't actually match, with these things, then you're going to get a wrong probability. But if these things are correct, then it's just a matter of substituting these things in the Bayes equation or Bayes rule with these numbers and then solving. There's a couple more things with the law of total probability and the multiplication rule that we'll see, because we don't have the probability of A, the probability of a positive test result. So let's go ahead and solve this. And we have, actually, let me just, so I keep this. Okay. So we start with writing down what our goal was. That's the probability of B given A. So we have let's put it here. The probability of B given A is what we're after. So let's use Bayes' rule. So this is the probability of B times the probability of A given B over the probability of A. And the probability of A is, we don't know. So we can fill in this stuff, right? We have that. We don't have this, so we're going to have to use the law of total probability and the multiplication rule to expand this out into individual terms. There's like a lot of stuff packaged in here. We'll unpackage it and then we'll be able to solve it. So let's start by doing just that. So this is going to be still the probability of B times the probability of A given B over, this now becomes the probability of A union B plus the probability of A union the complement of B, right? Because the probability of A is going to be the probability of B plus its complement. Now, where this intuition comes from, this might be helpful to go back to revisit this, is that we have some event A that occurs, and we have a sample space S, and we know that we have an event B. So for any sample space, if we have an event B, we know that we also have B's complement, which is whatever isn't B, is on this side. And that together these form partition, and the partition equals 1, which means it equals the entire probability space. So what we're saying is that if we have an event A that occurs here, there has to be some A that occurs both in B and the complement of B. Unless one of these are 0, and then the other one is 1. Sort of like a coin flip with a coin that's will always give you heads no matter what. Then this would just be, the whole space would be B. But A must occur at some level on both of these. So what we're saying here is that the probability of A has to occur across both B and its complement. So that's how we're able to take the probability of event A and break it up into these two forms. This gives us kind of the intuition behind that, hopefully. So, but yeah, unfortunately for us, we don't have either of these as well. However, now we can use the multiplication rule. So this was Bayes' rule, and then this was the law of total probability. And now we can go ahead and use the multiplication rule. So we still have the probability of B times the probability of A given B over, let's expand this further, the probability of B times the probability of A given B plus the probability of B's complement. Oh, well, let me redraw that or rewrite that. The probability of the complement of B times the probability of A given complement of B. And this is just the multiplication rule, which we saw allowed us to kind of expand this out from, this, and then through the law of total probability, and then through the multiplication rule, we can get this. And we actually have some of these things. So even though this highly packaged form, we started to unpackage it, we still don't have anything, we can unpackage it even further. So let's go ahead and do just that. And let's start by kind of filling in some of these colors. So the probability of A given B, we have that. That's right here. And we also have it down here. And we also have the probability of B, oh, whoops, wrong color. Probability of B, probability of B, and the probability of B. And we also have one other thing, the probability of A given the complement of B, which is down here. So the only thing we're really missing is this, which we will be able to intuit from these things. Well, really from this thing. So let's go ahead and let's, you know what, I'll say that I'll give this like a little box because we kind of have this. Okay, so let's start filling in some of these. And one particular thing to note as a insight that you are on the right track, that you're doing good, is that you have things in the numerator that you also have in the denominator, because that allows us to, make the math easy. Okay, so this is going to equal 0.1 times 0.95 over 0.1 times 0.95 plus, this is the probability of the complement of B. We know the probability of B is 0.1. So this is going to be 1 minus 0.1 times 0.15. And let me just highlight these again. So I'm going to say this is blue, this is blue, this is blue. Again, this is not really blue, but we solved it using the probability of B. So good enough for me. And then this is yellow, yellow, and then this is our green. So we have everything. So we can just simply do the arithmetic, and this is going to be about 9 times 0.15, about 40, let's call it 40%. So what this is saying to us is, this is our final answer. So if you test positive, well, let's actually rewrite, not rewrite, but let's get this. I'll have to rewrite this. So what's the probability that they use steroids? So that's what we're trying to find. So what we can say here is that if you test positive, there is about 40% chance you actually use. So why is that so much lower? Oh, I thought it was 95% chance of the time it works. Yeah, that's true, but 95% of the time it works is not the same thing as saying that 95% of the people who test positive on this test use steroids. If that's true, then it would catch people 95% of the time, and it would have 0 false positives, which means it would never test positive in the case where somebody didn't use steroids. But testing for steroids is a complicated process which involves blood chemistry and phlebotomy and all this other stuff. So it's going to have some false positives. So if you test positive on this test of steroids, there is about a 40% chance that you are actually a user. So most people who test positive actually don't use steroids. And the reason why that's, sorry, there's a loud car outside. And the reason why that's true is because of this right here. The probability of using steroids is already very low, 0.1. If this was high, like 0.6 or 0.5 or 0.8, then this number here would really change a lot. This number is extremely sensitive to this because ultimately this number is being used a lot and is a multiplier, and it's really what's going to jack up this rate through this multiplication here. So if more people use steroids and this test catches them 95% of the time, then and you test positive, it's much more likely that you actually use steroids. But because this rate's so low, it's less likely that you use it. Okay, well, let's go ahead and do another more difficult problem. Okay, let's do this one last example, and then we'll call it for this lecture. And we'll do more examples of these kind of problems in class, so don't worry. You'll get plenty of other examples to work through. So this one's all about taste testing burgers. Your friend claims to be able to correctly guess what restaurant a burger came from after just one bite. Quite the claim. The probability that she correctly identifies an In-N-Out burger is 0.55. And we'll just start going ahead and highlighting important things. So In-N-Out burger, 0.55. Shake Shack burger, 0.075. And Five Guys burger, 0.6. Okay? So those are the probabilities that we have for her correctly identifying a burger. We go out and buy 5 In-N-Out burgers, 4 Shake Shack burgers, and 1 Five Guys burger, because Five Guys burgers are a lot more expensive. So one of them makes sense. You choose one of the burgers randomly, and you give it to her. And the question is, given that she guessed, let me also, 5 In-N-Out, 4 Shake Shack, and 1 Five Guys. Okay. Given that she guessed it correctly, what is the probability she ate a Shake Shack burger? All right. So first of all, let's see. We're thinking about trying to determine which of these burgers was the probability that she ate at Shake Shack, that she ate a Shake Shack burger. So let's just start to jot these down. So we have 4 events in this problem. We have we'll use I to denote in and out. We will use SH because I don't want to confuse it with Shake Shack. Well, I also want to write an extra H too, so I'll just put over here. If I write that and I write that, this equals a probability space, and for this question, this will equal a Shake Shack. Okay, so S is Shake Shack, and let's go F for Five Guys, and then we will have C for a correct guess as our other event. And since we've already been given these, we have this 0.5, 0.6, and 0.75. We have those numbers that we'll make good use of because they have to do with the guesses that your friend makes for each burger as individual events. And then we also have the total space of burgers that we bought, 5, 4, and 1, so that's 10. So we can go ahead and begin to write down this information. So we'll say the probability of the random burger being an In-N-Out is 5 out of 10. So we'll say 0.5. And the probability of it being a Shake Shack burger is 0.4. And the probability of it being a Five Guys burger is going to be 0.1. Okay. Now then, we want to write our conditional probabilities. So that is, I always forget to, I guess it really doesn't matter, but my P's like that. So this is that your friend guessed it correct given that it is an In-N-Out burger. And that's going to be 0.55. And the probability of guessing it correct given that it's a Shake Shack burger, 0.75. The probability that it's a correct guess given a Five Guys burger, 0.6. And ultimately, what we want to find out, maybe we'll highlight this in green, given that she guessed it correctly, so given guessed correctly, what's the probability that it was a Shake Shack burger? So how can we write that? Well, that's the probability of a Shake Shack burger given that she guessed it correctly. So given that a correct guess. And this is what we want to find out. All right, so let's go ahead and work towards that. And there's no big surprise that this problem is going to be set up in a very similar fashion to the previous problem. So let's go ahead and bring this over here. Get rid of that rubbish. Okay. So let's think real quick. What does our sample space look like? That's always worth drawing. Well, our sample space is a partition because we bought burgers from 3 joints, and one of the burgers were randomly selected from one of those 3 joints, so it must be a partition sample space of the 3 burgers. So we will go ahead and just draw this. So we have Five Guys, we have Shake Shack, and then we have In-N-Out. Okay, so we have that picture, we'll need that. And we want to determine the probability of Shake Shack burger given that it's a correct guess. So let's write that down. So first thing we're going to do is use Bayes' theorem because what we have is sort of a reverse problem here, reverse conditional problem. Maybe I'll just write that as a little aside. So we have the probability of a correct guess given Shake Shack. And we can put that right here. But we want the inverse of that. What we want is the probability of a correct guess given, or of it being a Shake Shack burger given a correct guess. So Bayes' theorem is a natural tool that we can use. to solve that. So let's write the equation for Bayes' theorem given our probability of Shake Shack burger given a correct guess. That's the probability of a Shake Shack burger times the probability of a correct guess given a Shake Shack burger over the probability of just getting a correct guess. And that is the one thing that we don't have. We do not have this. So that's what we're going to need to figure out. We have to transform that probability of getting a correct guess and unpackage it. And the packaging, the contents of that package exist in these givens that we have. So let's go ahead and do that. We will use the law of total probability, and we're going to get the probability of Shake Shack burger times the probability of a correct guess given it's a Shake Shack burger over, this is where we get the expansion of the probability of a correct guess using this partition. So this is the probability of a correct guess and an In-N-Out burger plus the probability of a correct guess and a Shake Shack burger plus the probability of a correct guess and a Five Guys burger. So we can use the multiplication rule next. And I just set this aside. So this is through the multiplication rule. And we will expand out the denominator. And that's going to be the probability of a In-N-Out times probability of a correct guess given In-N-Out plus the probability of a Shake Shack burger times the probability of a correct guess given Shake Shack plus probability of a Five Guys times the probability of a correct guess given Five Guys. Now we have all this information all packaged nicely up there for us. And what's more, because we said that this was important, we see that there is a duplication in our numerator and our denominator, which is a telltale sign that we're on the right track. So now I can just begin to fill in this this information. So this is going to be the probability of a Shake Shack burger is 0.4 times the probability of a correct guess given a Shake Shack burger, 0.75 over 0.5 times 0.55 plus 0.4 times 0.75 plus 0.1 for Five Guys, because it only bought one Five Guys burger, times 0.6. And this will equal approximately 0.4 times 0.75 is going to be 0.3 because 75% of 0.4 is 0.3. So that's going to be 0.3 on top over 0.55 times 0.5, 0.255 0.4875, 1.6. So this is going to be about 45% or so. Again, that's not necessarily terribly important. Yeah, if you got this point on the exam and there's no calculators, you can just leave it, and that's fine. Though if you only have a final answer to something like this, then you could probably do that. But I'm not looking for perfection in arithmetic at this stage in the problem, because it's what calculators were invented for, to offload our cognition. So yeah, this problem is not terribly difficult in some sense. We have our partition space represented by these three probabilities here, and our numerator is taken care of. We went into Bayes' theorem. So the only thing we had to find out was the probability of a correct guess. And the reason why we couldn't just get that immediately is because that was all packaged into this information here, which we were able to extract out. And yeah, I think the hardest part here is translating this stuff into this stuff. Once you have that, then the next hardest thing is the multiplication rule and knowing exactly how to phrase these problems. And for that, you can look at your numerator and try and figure out, beyond just like looking at what makes sense. If you remember to this point here, you can use the multiplication rule to kind of turn your probability of A and B into one of these two. And I should actually write this a little bit nicer now that I'm looking at it. B. So in our case, we could have chosen the probability of S or C down here, but we're trying to figure out the probability of S given C. And so we already have the probability of S up here. We have that probability, so we should use this form because it makes it easier. Okay, that's it for this lecture. So we will go ahead and do more of these problems in class as we review for the final, because there's only a few lectures left. And this concept that we've built on getting used to Bayes' theorem, which we'll talk a little bit more of in class and think about it. We'll be able to use this as a way to work into the naive Bayes classifier, which is a way of classifying, for example, spam versus not spam. So that requires a lot of probability calculations. So this is where all this is building up towards, this intuition of probability. Yeah, it's good stuff. Okay, we will see you in the next lecture.